All right, the next video in day 2 of neural networks is to talk about forward propagation. So if you're, before we can talk about really forward propagation and sort of what's called the architecture. So architecture, hopefully I spelled this right the first time. Architecture of the network. So architecture, I guess I don't need that, of the network. All right, I know we haven't really started. I mean, we've had these little circles and we've moved things in here, but we really haven't talked yet about having multiple. Actually, we have had multiple input circles, but we've never had multiple outputs. And of course, this is the first time that we talked about hidden layer. And in class, we'll discover why we need hidden layers because they're basically make it so you can have curves. So that's the idea behind that one. So, or that's the reason why you have to have hidden layers and then the sigmoid functions so that you can have nonlinear curves that separate the data. Okay, so this particular architecture is 3 by 2 by 4. And what that means is I have 3 nodes in my input layer, not including the bias, right? So that's why you label it 1, 2, and 3. And 0 being the bias. So x0, so always 1's always going to come into here, and then whatever your input vector is. This is not this is not x sub I. The nomenclature here, and you can see it down here written in the table, is the input to the input. So the input vector xi1, xi2, and xi3 is the input to the input layer. So that's the input vector to the input layer. And there's going to be however many nodes I have is usually determined by the problem. In this particular case, we're just saying that we have 3 nodes in the input layer, so my vector needs to be a 3 row by 1 column or a 3 by 1 column vector. So you can see x of I here. Okay, and then a hidden layer has because of this number 2 here, the hidden layer has 2 nodes associated with it, not including your bias node. Again, 1's always going into the bias node, so we don't really concern ourselves with that piece because I don't need to calculate the number that's going into the hidden layer here. And then the final layer you can see has 4. Again, this is also determined by the problem. For example, when we go to try to classify 9 different or 10 different things, we're going to have obviously 10 different output final, I should say. So real quick, most of the time in the literature, you'll see this called the output layer. I did not want to label it that just because I have output vectors and input vectors, and I just didn't want to have an input to an input vector and an output to an output layer, output vector to an output layer. I just wanted to sort of try to separate that. And I probably should have renamed this as well. Maybe I should have. Anyway, bottom line is, we're going to call this the final layer, this last little piece here, and it doesn't need a bias because you're not feeding another layer. So this will just have 1, 2, 3, and 4 in this case because it has 4 nodes in it, and whatever comes out of here would be OF 1, 2, 3, and 4. So this last vector will be a 4 by 1 column vector of outputs. And so what forward propagation does is I'm sorry. And then every single one of these nodes that connects a node from the input to the hidden or a node from the hidden to the final has a weight associated with it. So as you can see, the node 1 connects to both of the nodes in the hidden layer, and node 2 from the input layer connects to both of the nodes in the hidden layer, and node 3, and so on and so forth. You have this full connectivity of all the nodes. In other words, we're not taking off one of the connections in any case. And so what that leads to is a W01, a W02, a W11. So what does the O1 stand for? It means from 0 to 1. This O2 means from 0 to 2. The 11 means from 1 to 1, and so on and so forth. You can see every time I label it, whatever number comes down here the first one is the previous node number, and the second number is the next node number, and then whatever the next layer is. And you can see that same way of doing business, that same sort of trend should say trend, the same nomenclature is used in the next one, right? So 0, 1, it goes from 0 to 1, and 1, 1 goes from 1 to 1, and you can kind of see how that works. Okay, with all that being said, what we want to do with forward propagation is simply just give me an input vector, right? Whatever, however many nodes you have here, and that'll be, so this will be a 3, let me move that. This will be a 3 by 1 input vector. And what forward propagation does, now there's a lot of sort of calculations that goes on here, but we'll talk about each one of them. What it does is it moves from this input vector and it moves through the network and it creates an output vector. In this case, will be a 4 by 1. Okay, the question is, how does it do it? So that's the whole purpose of this video. Now, fortunately, the first step is fairly simple. So to go from the input layer of the input, the input vector of the input layer to get on the other side here, in other words, when it goes through these nodes, it doesn't do anything. These nodes do not have an activation function associated with them. So all we're going to do is set xi, your input to your, I shouldn't do this with an I, not capital I, but big I. So this is a capital X and an I equal to the output of your input layer. So these are basically equal. They're the same. And I guess I'll write that. So they're the same. And then the next thing is, well, how do I get, so that's what's coming out of the nodes here. But the next question is, how do I use these weights in order to get the output of this node, or the output of that node, or whatever it is? How do I get it to be the input? And notice that you go from 3 to 2 here, right? So I got 3 things, and I need to turn it into 2. So let's just look at here. Let me choose a color here. Let's just look at kind of what's going on. So I'm going to circle that sucker in yellow, and we're gonna do it. So we're going to call it X. Why am I calling it X? Because it's the input to the H layer. In this case, H being the hidden layer. So it's XH. I'm not going to use vector notation just yet. And that's going to be what? Well, what's coming into this node? Well, just trace it back. Well, W01 times 1, right? So I can just put W01. Simple enough. Plus, right, what else is coming in? Well, this little arc here represents the weight W11, and then I got to multiply it by XI1. Not XI1, but the thing that's coming out, this OI1, right? Because we just said they were equal. So it's let's see, W11 times OI. Let me make that a little bit bigger so it's not a subscript. The OI1. And then the next one is, okay, what else is coming in here? So I've taken care of this one, and how about this guy, W21? So it'll be W21 times OI, and that's OI2, right? Because that's the number that's coming out of there. And then plus, so we've taken care of that one, and then that's the 3, right? So it's is that 31 times OI3. Okay. So that's the calculation. That's how you get 8XH1, right? Because that's the number right here that's going in. So we'll call it XH1. And then the number that's going into here to be X. Let me use a different color just so we can differentiate between the two. I don't know. I like this pink. So the XH2 is the number that's going into this node. And I will just circle it with pink. And we will XH2 is equal to, again, do the same process, follow it back, WO2. So it would be WO2 times 1, but we don't need to multiply it by 1 because we know that that's what's coming in there every time. And now we trace this guy back, and it's W12 times OI1, right? So that just go back and see that OI1 is the one that's over here. And then plus W, and see which one is the next one, 22 times OI2 plus W, and you can start seeing the pattern here, hopefully, because we're going to need the pattern here in a second. OI3 3, right? Because that's the number, OI3 is the one that's coming out of here. Okay, so wouldn't it be neat if there was a easier way to do these calculations, right? Because, I mean, certainly we could program the computer to knock this out, but fortunately for us, there's a easier way to do this. I'll call this XH1 and XH2. And that's going to be equal to, so this first piece is just W01 and W02, so it's a vector. It looks like this, W01, W02, and then plus, I'm going to turn this into, a matrix. So what does that look like? So what does that matrix look like? Well, it's W11, W21, W31. So it'll be W11, W21, and W31. And then the bottom one would be W12, W22, and W32, all times OI1, OI2, and OI3. So all times this thing. OI1, OI2, OI3. Okay. So with that, checking that sucker out, hopefully that makes sense to you how I ended up doing that, right? Because now if I did XH1, it would be W01 times W1. I mean, just this matrix multiplication gives you that top, this exact same row up here. And the bottom row, this row times that column gives you the what's in pink. So another way of writing it, right? Again, you know, of course, we want to sort of simplify our notation because we don't need to write this every single time. But XH, so remember, this is input to the hidden. So this the numbers that are on this side is equal to, and we're going to call this guy, what is it? I bias. So it's the input bias vector, meaning it's just these two numbers. Plus, now, what you have to recognize, well, you don't have to, but hopefully you recognize that if I was going to give you a matrix, here, let me just kind of write it somewhere. Let me see where I have space at. Let me put it in green here. So if I give you a matrix A and it's let's just say it's 2 by 2, this would be the component 1, 1. This would be the component 1, 2. This would be 2, 1, and this would be 2, 2. Now, if I do the transpose of A, that's where you get A11, A21, right? The transpose is basically takes the rows and turns them into columns, and so that would be this column would go down, so A1, so this row would turn into this column, and this row would turn into that column, so then A22. So recognize what's happening here, right? So because of the way these are numbered, I just wanted to keep them the same as sort of linear algebra, right? In other words, if we want to call this matrix WIH, meaning the W's that go from the input to the hidden, and I wanted to create it so that all of the naming conventions that we've talked about so far were correct, and oh, by the way, it matches up with what, you know, how we designate subscripts in linear algebra. In other words, that stands for row 1, column 2, and that stands for row 2, column 1. I want this to be row 2, column 1, right? So that's, in other words, I want this will end up being the WIH transpose. So that's the whole purpose of me sort of going through that business. And this will be just OI, right? And so let's just write out. So this is a 2 by 1. Let's just make sure all this stuff fits. So that'll be a 2 by 1. WIH itself will be a 3 by 2, right? Because I have 3 over here and 2 over there. But if I took the transpose of it, it'd be a 2 by 3. So this would be a 2 by 3. And OI would be a 3 by 1. Which this matrix multiplication, right? So those have to match up, and it ends up being a 2 by 1 plus a 2 by 1 would give you a 2 by 1. So at least the dimensions match up as well. All right. So now, once we have this, what do you need to do in order for it to go through these nodes? Remember, we have this activation function that we talked about earlier. So if you went up and you started, or went back to last video, you would know that in order to, so unlike over up here where I was just setting them equal to, it's no longer that. I have to do an activation function in order to get the output of the hidden layer is going to be equal to the sigmoid function of each one of these individual components. So in this case, it'll be what, xh1 and xh2. So all the sigmoid function just acts on each one of these components, or the sigmoid of xh. So that's the activation function, if you will, that we're using for this one. Okay, we're almost, I think we're almost home with forward propagation. I don't want to go too far down. All right. So now what I want to do is the same business except for, let's see, let's try another color. I did pink. Let's do peach. So again, it's doing the same kind of business here, right? So I'm going to just call this will be the input to the final layer 1, right? So node 1, and it'll be equal to, well, just trace yourself back, WO1 times 1. So WO1 plus, let's see, W11 times X1 plus W, let's see, 1, let's see what else is coming into layer, or here it is, 2-1. 2-1 into X2. Ooh, no, it's not X. That would be true if it was, this would be output of the hidden 1, output of the hidden 2. So it should be something like that. And then let's see a color I haven't used yet. Green would be that guy. So again, we're trying to find the number that goes into here. Control Z. Control Z. Yeah, I'm just gonna, so we're trying to find the X F2, right? So that's what that sucker is. X F2 is equal to WO2 plus W12, make sure that's right, W12, so 1 to 2, OH1 plus 2 to OH2. And then this one, XF3 equals WO3 plus, I probably should have put those together. Matter of fact, let me do that. Let's put them right up underneath each other. I'm going to run out of space if I don't. And then WO3 is W. So if that's 1, 1, and 1, 2, this sucker must be 1, 3. If that's OH1, OH1, this must be OH1 plus 2, 1, 2, 2. You know, it's hard. It's not hard to figure out what the pattern is after you see a couple of them. Let me just make sure that's right. So 1, 3, yep, with OH1, and then 2, 3 with OH2. All right. And then the final one, I'll do this sucker in purple, XF4. And I'm only doing this just so you guys see it multiple times. You can fast forward through the video if it already makes sense to you. OH1 plus W24OH2. Okay, so again, same idea. I wish there was a easier way of doing this, and guess what there is. So we're going to let XF, so the output, the input to the final layer is simply equal to, I'm going to call it H bias, and it's a vector. In this case, H bias is this W01, O2, O3, and O4, so this stuff. And then plus, again, this is the WHF matrix transpose. So we're talking about this one, and transpose, that would be a 4x2. This would be a 4x1. And then I'm multiplying that guy by the output of the hidden layer, which would be O output of the hidden layer, which we know is a 2x1. So if you do this multiplication, you get, I was just doing this. So 2 by 2, these match up so that it becomes a 4 by 1 and a 4 by 1. So this guy ends up being a 4 by 1. So that is the X's that go into there. And the final thing you do is the same thing that we did above. If I want the output, which is what we're looking for, the output of the final layer is simply equal to the sigmoid of the input. Right, because we're going through these nodes, and that's an activation function. So it will come out as, in this case, we'll just let it be OF1, OF2, OF3, and OF4 for this case. All right, so again, sort of nomenclature here, the input vector and the output vector for each one of the layers, and you're moving from here to here, then to there, then to here, then to there, then down. Okay. If you were in class right now, I would ask you if there were any questions, but of course there is not. So we will move down and to sort of summarize what's going on here for this particular. So at the last lesson, you can just sort of stop the video here and kind of read these out. But the bottom line is, I mean, step one is to just set O equal to X, O sub OI equal to XI. And then step two is XH is equal to I bias plus the WIH matrix transpose. Remember, these are the model, WIH and WI bias, WIH, H bias, and WHF. Those are the things that carry weights, and those are the model. That's what you're updating every single time whenever we get the error and trying to use error to update those things. But again, that's the model. So you're using these weights in order to forward propagate all the way from starting at XI all the way through XF. Okay, so then we go to the output of the hidden layer is simply the sigmoid of that guy. And then the next one is to take this one, I'm sorry, OH, to take OH and then multiply it by the transpose of WHF transpose, WHF transpose times OH plus the H bias gives us our input to our final layer. And we take the sigmoid of our input in order to get the output. Okay, again, that's it. Hope you guys got something out of this one. We'll talk about error, back propagation of error here next class or next video.